Hello, lovely humans. Jen Foxbot here. In this third installment of our Math Mondays foray into machine learning, we are going to look at gradient descent. Yay! In other words, this is a more efficient way to find the minimum of the cost function, which is the difference between our actual data and our best fit line. So we're going to use gradient descent because we don't want to find that minimum by hand. And we're going to use a fun math trick. So put on your thinking caps and start to think about what math trick, hint, it's in calculus, we might be able to use to find a minimum. Okay, so let's dig into it. Gradient descent. Yeah! It is an algorithm for minimizing our cost function, which is basically just a measurement of how close our predicted values are to the actual values. I don't know why we use J, but we do. It makes me happy because Jen, haha. So I'm going to stick with that convention. J is our cost function is some function of our parameters. In this case, we're just doing 2 dimensions, but you can have gradient descent work for any number of dimensions, which is awesome. So let's say we had theta of n, where n was 300 million. You could totally do that with gradient descent. It would take a lot of compute power, but you could still do it. So yay for gradient descent, which is going to be code that does the minimum for us. Yes, even better. So the general procedure for doing gradient descent is one. Well, I guess the goal. So let's write some stuff down. Okay, goal: find min of our cost function. Okay, that's our goal. So what we're gonna do is we're gonna pick theta naught, theta 1, and if we have multiple parameters, we just pick values for those. Often they're randomly initialized. Then we are going to look for the downward gradient. Okay, I was going to say slope, but gradient is a more technical term. And the downward slope can also be thought of as the steepest. So, for example, if you were looking on a topographical map, you would be looking for the lines that are the closest together, because that would tell you where the land is the steepest. Okay, number 3. So once you've found the steepest gradient, then you pick new values for all of your parameters. And hey, and then we really just repeat 2 and 3 until minimum. Cool. Well, I should say local minimum. That's important. Okay, so that is our general procedure. And so this would be our algorithm in kind of pseudocode. And we would repeat this until we converge at the local minimum. Okay, so I'm going to use some more pseudocode to help us throw my eraser on the floor. Oopsies. Okay, to help us figure out how we would actually implement this as an algorithm. For that, I need more space, so we're going to erase this. And we are going to define how we would convert our procedure into a mathematical formula. Okay, so we are going to start with some value of each of our parameters. I'm going to use the subscript j, yay for j, to just basically say this is one of our parameters, and we need to update this using the old value. So you can kind of think about this as like, this is the new value, and this is the old value. And this old value is going to change based on the mathematical technique for finding the slope of a line. Hey, what are you thinking? What can we use? Well, first we're going to have a constant, and then we're going to multiply that constant by the derivative. Yes, derivatives. So useful. In this case, we're going to take a partial derivative with respect to that parameter, and we're going to take the partial derivative of the cost function. So j of theta, I'm just going to write two parameters for now. So in this case, we would have j equals 0 and j equals 1, where j is the total number of parameters that we have in our cost function. So you could have 0 through n, where n is 350 million. And if we have code, it's not that big of a deal, right? Well, at least to write the code. Less trivial than writing it on paper, that's for sure. Because I can just write a for loop and just set the for loop to iterate 350 million times. It's probably going to take a while, but still faster than writing on paper. Okay, so this pseudocode symbol is the assignment operator. So this is just this right here, this colon equal sign is just saying the new parameter value is going to be set to this equation minus the stuff in blue. That's not part of the equation. And it is equal to the old parameter minus the learning rate, which is just a constant that determines how big of a step we're taking, how much the derivative is going to impact this subtraction from the old parameter. And then the derivative is what tells us basically the direction to go. I should say partial derivative as well. Okay, so what we want to do is simultaneously update each of the parameters. So the correct way to implement this in pseudocode would be to write something like, we're going to have a temporary variable to hold the change between the new and the old, because we don't want to wipe out our variable when we need it. So we're going to have temp0, which is just a temporary placeholder for our first parameter. And we are going to assign that to be equal to theta 0 minus the learning rate times the partial derivative of j theta naught and theta 1. And then we want to do this for each of the parameters. So in this case, I'm just going to write two of them. So then this would be the temporary placeholder for theta 1. And that's going to equal theta 1 minus j partial derivative of theta j of j theta naught, whoops, and theta 1. There we go. Okay. So you would find the partial derivatives, subtract it from the previous value, and then you update your parameters. So then you would say theta naught is equal to temp 0, and theta 1 is equal to temp 1. So it's really important that you do this first before you update any of the parameters, because if you were to update this in between, when you take the partial derivative, you're gonna have a different value of theta naught here, and that's gonna totally mess up the equation because you're working with, your numbers are basically inaccurate. So it's gonna throw off your whole algorithm. So let's not do that. We want our machine learning algorithm to be accurate, right? So we're gonna take all of the partials first and then update. And we're really just gonna iterate through this until we end up with a minimum of the cost function. Okay, so the derivative gives us the tangential line of a function, and the slope of that tangent line is the derivative of that point, and it gives us a direction to move in. So for example, we're gonna draw some pictures. Yay, pictures. Okay. So I'm lazy, I'm just going to draw in one dimension. So we're going to call this theta 1, and this is j of theta 1. So we have some curve here. So let's say we pick theta 1, and we end up at a spot right there on the curve. When we take the partial derivative, we're going to get a tangent line with a slope like that. And so because this is a steep slope, we are going to subtract that from our first point, and then we're going to move down the slope, and then we're going to do the partial again. We're going to get a slope that's smaller than the first slope. So if I pull these out to make them a little bit better to see, this first line is steeper. Think about if you were on a bicycle going down these hills. You're going to go way faster on this hill than on this hill. And as we move farther down the slope, or sorry, farther down the curve, I guess the slope of our curve, our tangent lines are going to get even smaller. Or I should say our tangent lines are going to get even flatter. Yeah, there we go. Until we have a horizontal line. Yes! Okay, and so this is our minimum. What does it mean to have a minimum? Well, it actually means that the partial or the full derivative of j of theta with respect to theta is 0. Woo! Because a flat line doesn't have any slope, so its slope is 0. So that's how we know we have minimized the cost function. The steps as we move down the cost function is going to be the steps are going to be in the direction of the steepest descent, and the size of each step, so the distance between each of these points, is determined by alpha, the learning rate. So if we have a smaller alpha, we're going to have smaller steps. There's a balance to be had here. You don't want too small of a learning rate, because then it's going to take forever and we don't have that much time. Our lives are finite, so let's enjoy them. And you don't want it to be too big, because let's say I'm here and my learning rate is really large, I might accidentally jump over to this side of the curve, and then I'm going to end up jumping back, and I'm going to basically oscillate about the minimum without actually being able to get to the minimum. The other thing that's really interesting is that even though the learning rate is constant, because the slopes of these lines are getting smaller, this whole term, I'm going to use my other color in my, I knew there's a reason I was holding this still. So this whole term, as the derivative gets smaller, that whole term gets smaller. And so we subtract less and less from our previous values. And so our step size automatically gets smaller, which is helpful because we, again, do not want to overshoot the minimum. It's easy to miss the minimum. Okay, let's see, what else do we want to do? Dun, 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 dun. Okay, so, the last thing I want to mention, there's a couple of kind of mathy stuff in here, but I don't think it's super useful. Yeah, you basically, I'm being lazy and using a placeholder for j theta for the cost function, but you could actually, we know the equation for the cost function, so you could insert that equation into here and then actually write that out to get an idea of what the equation would look like. But you can plug and chug, I trust y'all. So I'm going to skip that, and I'm going to end with a comment on batch gradient descent. So this is the type of gradient descent that uses all of your training examples. So if you have 100 training examples, you would do gradient descent with all 100 examples. Okay, so I'm going to leave it there for now. Gradient descent is really just taking partial derivatives of our cost function. And again, our cost function is probably going to be a lot more complicated. It's going to be something like, I don't know, a bowl or whatever. Yeah, cool. This is 3D. Okay. It's probably going to be even more complicated than that. It's going to have like all sorts of all sorts of curvy, wobbly, wiggly parts. And so batch gradient descent helps us to figure out where there's a local minimum that will be a reasonably accurate model of our data. And we can write it into code. Yes, so fun. Way easier than doing it by hand. Okay, thank you very much for watching. If you found this helpful, please remember to like and subscribe and share the video with your friends. It makes me really happy when more people are able to learn from these. It also means that more people get to make requests of different types of content and help each other out in the comments, which always makes me, it always warms my heart to see that. So thank you everybody for your positive contributions and for being such wonderful people. Okay, I will leave it there for now. Thanks again for watching, and we'll see you next time. Bye!